Frans Oort and Steve Schatz, who was a student of John Tate. So Steve.
So I just want to take a minute or two and not describe anything that Frans is going to talk about, because Frans is going to talk about what he wants to talk about. But I believe that Frans is going to tell you something about why John Tate won the Abel Prize, as opposed to, John Tate is a nice guy. and the issue is that there are very few people who have written papers with John Tate. Among the reasons for that is that John Tate is not in general a paper writer. He may do a lot of mathematics, but he doesn't write stuff down. And he writes even fewer things with people. And Frans is one of the very few people who actually has a paper with John. Okay, and so of all the people right here, and probably in the whole Philadelphia area, and maybe even the eastern half of the United States, I can't think of anyone better to talk about why John Tate won the Abel Prize than one of his co-authors. So Frans, go to it.
Thank you very much. Well, I thank the organizers very much for giving me this chance to talk about this wonderful person. So thank you very much for that. I think in our professions we really have to cherish all the pioneers and the people who gave us so many beautiful ideas. So thank you very much for giving me this opportunity to say something about John Tate and about his work. But let me first state that I'm a little bit shy, because Steve was one of the PhD students, but also Ted Chimber was one of the PhD students. And so when this came up, I suggested to Steve or Ted that they should give the talk. But for some reason, either they were polite to me or for some other reasons, they said that I should give the talk. So, okay, thank you very much, Steve. Thank you very much, Ted. And I'll try to do my best, but you may have some additions to what's going on. So, the title of my talk will be that John Tate received the 2010 Abel Prize. And in my talk there will be two parts. The first part, which is the smaller half, if you would say that, I'll have some personal memories to John Tate, and I'll tell you what kind of kind person and what kind of really nice person he was. And then in the second half I will give you one example of a notion coined by John Tate, which is kind of a basic example of why he got his prize. So I'll get into more detail. So the first half will be on John Tate as a mathematician and as a person. So that will be the first part, and the second part I will explain is one mathematical concept. And that mathematical concept, I really do hope that everybody in the audience will understand the pre-knowledge of this idea, the prehistory, and then where John Tate really intervenes importantly in this. So let me first tell you a story. Andrew Wiles was born on the 11th of April 1953, and as you all know, he worked on Fermat's last theorem, then had a proof, and told everybody, told the whole world that he proved Fermat's last theorem. And then, of course, in the process of refereeing, there was a small bug which couldn't be repaired, and it took him some time. And then, on the 19th of November 1994, he produced finally the correct proof. But that was too late, because the International Congress was before, and as you see, Andrew Wiles was not anymore under 40 when he finally proved the theorem. So all of us thought, what's going to happen? Will he get a field smell, or will he not get a field smell? And every time I give a talk or a course on this, I give the audience an exercise. Suppose you're in the field smell committee. What are you going to do? Break the unwritten rule that the field smell winner has to be under 40, or are you going to do something else? And the solution they found, I really think, was extremely elegant. They created a new medal, which was the silver plaque, and they awarded that to Andrew Wiles, and I think this is marvelous because they firmly established a rule that Fields medalists should be under 40 when they find their main result. But also now they have a new gadget to hand out to someone. So if some of you is feeling old, that proves the Riemann hypothesis, there is still a chance for getting some really big prize. And I think this is a brilliant idea. Okay, but there's no Nobel Prize for mathematicians, at least not for mathematicians, for mathematical topics. Of course, mathematicians who do economy or something like that.
Oh, yeah.
They can, you know. And so for that reason, the Nobel Prize not available. There was a prize which is written here. I hope you can read it. And I also do hope you can pronounce it. If you come to Norway and you talk about the Abel Prize, they will not understand what you're doing. The typist was typing my manuscript and she couldn't read my handwriting. Usual for everybody. And then she asked what's written here. I said, Abel, Abelian. And she had no idea what it was. And there's a big statue of Niels Henrik Abel in the midst of Oslo. So then I explained. He said, oh, you mean Abel. So in Norwegian, this is the Abel Prize. And why did John Tate get this prize? The first sentence the committee said was for its vast and lasting impact on the theory of numbers. And then they said, many of the major lines of research in algebraic number theory and in arithmetic geometry are only possible because of the incisive contributions and illuminating insights of John Tate. And that's the theme of my second half, that I really show you that the ideas by Tate, the tools he created for us, that's something which really is the main thing. So, the tools he created. You see, the screen is a little bit too short. So, certainly you're missing the looping Tate groups, you're missing Tate cycles, you're missing Tate twists, you're missing Tate curves, and then the rest is here, and well, there are many more. I mean, there are many concepts, many tools, many deep insights which Tate knew how to coin in a concept, in a technique, in a method, and that really gave us a completely new grip on mathematics. So John Tate was born in Minnesota, and it was nice. It's nice for you to go to the webpage of Minneapolis, where he was born, because the Minneapolis website really shows all the famous people born there, and John Tate is one of them. And just on top of him is a pop singer, and just below him is a wrestler. So he's going between the wrestler and the pop singer as one of the famous people born in Minneapolis. Someone said, oh, you're going to talk on John Tate? Of course, and the only thing you can do is talk about his PhD thesis. It's a marvelous piece of work, and there's something which Tate did, and Steve already mentioned this. He was very slow in really writing down and publishing things. So his thesis, PhD thesis, which widely circulated, was only many years. In 1950 he wrote, in 1967 it was finally published. So that could have been a topic for a talk like this, but let me choose another topic. So he was at Harvard for a long period of time, and I'll explain you why he was at Harvard for a long period of time. Then after retiring, he went to Texas, and now he's back in the Boston area, and now he lives in the Boston area. He's healthy and well. 2 or 3 weeks ago, I heard somebody who was on a conference, big gross, and he said, I'm not teaching my linear algebra class because John Tate is substituting me. So he's well and alive, and when you write to him, he will write back, and that's really fantastic. So, first, the topic which Steve already mentioned. He's a very modest person, and he did not write and publish easily. I have always found it a fantastic thing if you saw Jean-Pierre Serre and John Tate together or separate. John Tate would lecture, and then in the middle of the lecture he would walk in front of the blackboard and tell, what am I trying to say? He had enormous intuition, he had an enormous grasp on mathematics, but to coin his ideas, really his deep ideas, immediately in words, in sentences, and in plain ideas, that is difficult. Whereas Jean-Pierre Serre, I think you and I have the feeling if Serre has an idea, it comes in the way he will publish it. You know the wonderful story about the conference where at the night they were sitting in the bars, 3 people, and they fantasized, well, if this and this and this is true, can we prove that and that? And they went to bed, the other 2, and the next morning they found under the door a manuscript typed out, ready for publication. So that was Jean-Pierre Serre. Tate was completely different. His ideas came lightning speed, the basic idea, but to coin it and really to have it in a form which you can publish, that came very slow. And then when it was there, he didn't want to publish it. Because perhaps you can do it better and you can do it more generally and so on and so on. And I've witnessed that and I've drank that prize. So that was that. That cooperation resulted in a lot of ideas, the Tate, canonical arguments and so on and so on, and resulted in a beautiful publication, Good Reduction to Varieties, which is the most cited on Tate list. When Tate went to Harvard, let me first. When Tate went to Harvard, I want to tell you a story about this, how he became full professor. And I was a little bit shaky about the story, but Steve luckily said I was correct. John Tate was at Harvard. He got to Harvard when he had only 5 lists on his publication. So all of you who have only 5 publications on the list, don't desperate, just write to Harvard and they'll take you. If you're the level of John Tate. And then Emil Arti, who was thesis advisor of John Tate, retired, and Tate was offered a position at Princeton. And of course that was very tempting to become full professor and successor of the big Emil Arti. And Zariski got the air of this and immediately said that we have to take John Tate here. Now, Zariski was a wonderful person. He doesn't live anymore. He was really wonderful. He was very stimulating for all the young people. I'm seeing sitting him there as all these fields medalists. He said, oh, you're such a nice boy. You prove so many beautiful things. Difficult for me to understand, but it's fantastic. So he was that kind of person. He heard about this, went to the dean and said, listen, we have this wonderful mathematician John Tate, we should give him the full professorship immediately. Okay. The dean said, okay, can you show me his list of publications? And there came a list of publications, which didn't seem enough for a full professor chair at Harvard. So what Zariski did, Zariski rounded up all assistants, including Steve, and he pushed them in the library. And he said, you're going to collect all papers which refer to unpublished work of John Tate, which thank him for unpublished work, which say that it should be published, joint with him together, and so on and so on and so on. And at the end of the week, there was a long, long list. And from that moment, happily, John Tate stayed at Harvard. One thing for which Tate is really known is that he proved beautiful theorems, but conceptual concepts, that was something which really was the center of his value for our profession, for us as mathematicians. And I've chosen one topic. I will tell you how classical theory produces the concept of a period lattice. And I'll explain what it is. So that's a complex analytic tool which is extremely fruitful and which has produced a lot of theorems. But then I'll also show you that if you want to do algebraic number theory, the period lattice is of virtually no use. It is very nice in analytic theory, but in number theory it is of no use. And then Tate had a wonderful idea to substitute the period lattice by the Tate module. So I'll introduce later the period lattice, I'll introduce later the Tate module, and then I will explain you how classical concepts were transported into this new concept, in this new theory, and how it really changed our whole world. Before going to the next talk, the next half, I would tell you one joke about John Tate. It was always a pleasure when he was around. When David Mumford and I were working, he would look around the door and said, "Oh, you, aren't you proving anything?" And he would walk out again, because he wanted to keep pace with what everybody was doing. His love for mathematics, his love for beautiful structures was always clear. It always was conceptually very deep when you were talking to him. It was great to see how his ideas developed. I mean, some mathematicians had just close a book, and if you ask them, they only talk to you when the paper is finished. John Tate was exactly the opposite. He would really talk on ideas, on concepts, on what he was trying to do, and so on and so on. So he was wonderful. Now in 1967, there was a summer school in algebraic geometry in Bowdoin College, and there was a beautiful atmosphere. I mean, algebraic geometry was blooming, new ideas were coming, and David Mumford was going to give a whole series of lectures on the only varieties. David Mumford once lectured at Harvard, and one of his students made a remark, and David Mumford was really taken aback, because this is something he didn't think about. And then he looked at it, this was John Tate, he said, "Oh, it's my best student." So John Tate was sitting there and in the summer school, and David Mumford started writing down all things you had to know before you could follow the rest of the talk. And everybody was really getting depressed, because that is too much. I mean, there was no chance of knowing all these things. And so the atmosphere was really depressed. And all of a sudden, one of the chairs banged, and somebody walked down the stairs, went to the door, and with the door in his hand said, "David, I don't know these things, so I'm better going." That's what John Tate. Now mind John Tate, he was at that moment was really one of the heights of his knowledge, and he was one of the most respected algebraic geometers and number theorists around. He didn't know these things. So then David said, okay, I'm going to explain them. And that was it. So that was John Tate, a person who was really extremely nice, who was always ready to explain things, who was outgoing in his mathematics, but he was very modest, he was engaging, he was really stimulating for everybody. So this underlines my big pleasure that I felt when John Tate got the Abel Prize. So this is John Tate now. You remember the picture we had in the beginning? That was not his age now. I mean, this is John Tate in 2010. Okay, so you're not coming here because you want to hear only stories of an old man, but you want to hear mathematics, I suppose. So I had to choose, and I had to choose one topic, and so the topic I chose was something which lives in arithmetic geometry. So what is arithmetic geometry? You have number theory, and number theory is about equations, and equations give you curves and surfaces and so on and so on. So there's a geometric side to number theory. And one of the most fruitful ideas of the last 50 years, think of André Bruijl, think of many other people, was to go back and forth between the number theory and the geometry. You remember that very old technique, which was already 23 centuries ago. If you have a cubic curve and you have a rational point on it, you can produce a new point by taking the tangent line. It's a cubic curve, so it has 3 intersection points. The tangent line counts for 2, so you get a 3rd intersection point. So that's a way to get lots and lots of intersection points. And if you write down formulas like this, they're gadget of formulas which are very difficult to understand. For example, if you know the topic of congruent numbers, you can produce new congruent numbers, new presentations of one congruent number by this method. But that mechanism is really easy in geometry, but very difficult in algebra. So that's what arithmetic geometry is about, and I'll talk about field spaces and Tate models. Okay, so let me start defining the Abelian variety. Abelian variety, I have a ground field, and you may think of the real numbers or the complex numbers, but please, much better, think about a number field or a finite field. So any field you favor to think of at that moment. And the Abelian variety is defined over a field, and it is a projective group variety. So if you have a projective space of some high dimension, you have an algebraic variety in there, it's closed, and the points on the variety form a group, and the group laws, so the inversion, the zero, the multiplication, and so on and so on, are given by polynomial maps. So it's a group variety, it's a group, and this is a
If we don't do this for a living, what example would you like us to keep in mind?
Yeah, that's very nice. And you know, you always have to apply the Feynman method. Do any one of you know what the Feynman method is? The Feynman method, Feynman once was in Japan, and was a Japanese boy who explained to him the enormous theory in mathematics, and then all of a sudden Feynman said that this formula, it's on the board, is this correct? And it was incorrect. And this person thought, but this is God himself who's sitting there. So you apply the Feynman trick. The Feynman trick is, like Herman said, you take one example, and that example you have in mind, and anything which happens and which is wrong in that example is wrong. So, thank you Herman, I was going to that, and I'll get back on that. You take a cubic curve in the plane, that mine's projective plane, you suppose it's non-singular, and you choose one point. Then you can add points on that cubic curve, and all of you know how to do that. If you have a point P, you have a point Q, you want to add it, you've given a base point 0, then you connect P and Q into the third point, and you connect S and O, and here you write P plus Q. And what can be proved, it's not so difficult, is that this gives you a group structure on your elliptic curve. And actually, every Abelian variety of dimension 1 is an elliptic curve, and every elliptic curve is an Abelian variety of dimension 1. So that's an example, and actually the whole theory Tate developed already for elliptic curve is non-trivial, and is the key to, for example, Water's proof of Fermat-Laat theorem. Fermat-Laat theorem proof is unthinkable without the techniques which were developed by John Tate.
However, if you have complex eyes, just for the moment,
Yes?
you should think of points on the torus.
Yes, and that's
An ordinary torus.
so nice to have a marvelous audience. They immediately know what you're going to say. So a complex torus, what Steve mentioned, is something like this. It's homeomorphically to the circle. At times a circle. You can produce it by taking a cylinder and then paste the top and the bottom end to each other. And what you can prove, if you have an elliptic curve, you take the complex points, then this is isomorphic to the complex torus. And this will come back in my talk. So I'm going to produce for you the period lattice. So let me explain you what I want to do. Here I've made a picture of a Riemann surface, not genus 1 like this, but genus 3. And I have 2 points on it, P and Q, and I have a differential, holomorphic differential, and I want to compute the integral from P to Q of the differential. But you don't know how to go from P to Q. And maybe you go through a hole and then go one loop and then go one loop and so on, finally arrive at Q. So there's an indeterminacy in this thing here. And how do you do that? Okay, so to the being a variety over the complex numbers, we're going to associate a linear vector space L, which is a dimension G, the same dimension as your being variety. We're going to produce a subgroup, lambda, which is a lattice. A lattice means it's discrete, and if you tensor it up with the reals, you get the complex vector space back. And that lambda is what we call a period lattice. And the upshot of the whole thing is that if you take the L, which is this G-dimensional vector space, if you model out this lattice, you get a picture like this, if G is 3, and the values of this integral belong to this quotient. The lambda is exactly the indeterminacies souped up in some subgroup. Okay, now the beautiful thing is that L has a unique explanation, but the lambda has various explanations. And of course the strong point in mathematics is always if you have one concept which you can explain in many ways. You hop from one explanation to another to get theorems, to get proofs, and so on and so on. Okay, so L is the tangent space of your complex Lie group. Yeah, so you take the origin, then you take the tangent space, and that has the same dimension as your complex torus, as your being variety. And then from L to A, you have a map, which is the exponential map of complex Lie algebras. So that's integrating the tangent vectors along the Lie group. And if the Lie group is commutative, this exponential does exist and is unique. And it has a kernel, and the kernel is lambda. Now, because the image lands into a compact group and generates the compact group, the kernel is a lattice, a discrete subgroup also generates this vector space. So this lambda can be viewed as the kernel of the exponential map. So you think of the exponential map of the line, then the image is a circle, and the kernel is just the integers, e to the 2 pi I z. And here I'm not proving mapping to one circle, but to 2 circles, or 4 circles, or 6 circles, and we get a lattice which is there, the kernel. So that's one explanation. There's a completely other explanation. The map from L to AC you can view as the universal covering space. You see? This one you can unravel, you can write the plane and then map it to here by just modeling out 2 periods, right? And then you get the universal covering space. So the universal covering space of AC is some space which happens to have a complex structure, but that's not so obvious from this description. And of course the covering group is the first fundamental group. So the thing which is upstairs, the L and the lambda, can be seen as universal covering space and the fundamental group. And I really hope that you keep this picture in mind, because this will be crucial for the rest of my talk. So there are 2 things. Firstly, if you want to compute integrals, you want to take the kernel of this exponential map and so on and so on. And my God, what can you ever do with that in number theory? Now you change tactics, you realize that this lambda is a fundamental group. And so as soon as you know how to define fundamental groups algebraically, you have a definition of this. And if you would have this idea and a short piece of publication to enter Harvard immediately, that's basically what I try to say. Okay, so I explained the period lattice. That is what Abel did. So this was the beautiful idea by Abel. And that is the reason why these varieties are called abelian varieties. I mean, the group structure happens to be abelian, but that's not the main point. The main point is that Abel studied these integrals. These are called abelian integrals, and the values of these integrals for being Q given, but not the way to go from P to Q, such an integral has a value in L, and you just have souped up all the indeterminacies in this lattice. So this formula captures the first point of view, the point of view of Euclidean lattice. Okay, here's a special case, elliptic curves. You follow, of course, permanent understanding. Do we know how this works for elliptic curves? Oh yes, Varieties already did long before. Varieties defines the curly P Varieties P function. I'm not going to write it down. It's a long formula. And that Varieties P function satisfies a differential equation. And so it follows that if you take P and the derivative of P and 1 as 3 coordinates in the projective plane, then these 3 coordinates satisfy some cubic equation. So the image of this is just an elliptic curve, and that's exactly this map. So this map you can view as P prime ratio 1. Yeah? And in this way you obtain an elliptic curve, and what Varieties really proves, but that's non-trivial mathematics, that's deep mathematics, is that if you give yourselves a being right dimension 1, you can embed it as a cubic curve. Then by change of coordinates, you can embed it in this form, this is G2 and G3. Then you can produce a lattice in C, a period lattice, such that for that period lattice, the Varieties P function will actually give you this curve. So, already long before complex Lie groups were around, Varieties did the whole theory we did before, already for dimension 1. Okay, so we get an analytic parameterization. And now think for a moment. If I look into your eyes and you give you the sine function or logarithm or the exponential or any of your other transcendental functions, and they ask you, do you know if I substitute 3 over 4 in this, do I get a rational number or a transcendental number or an algebraic number? Or more generally, if I want to know all rational values of this sine function, do you know all things where it starts, and so on and so on and so on. And the basic issue is, 19th century mathematics, they were very concerned about algebraic values of transcendental functions. And one of the Hilbert problems was about that, and Hilbert thought this was the most difficult problem you can imagine, right? And there's still lots of unsolved problems on that side. And the big issue is, you can virtually say nothing about algebraic values of transcendental functions. You see this map here, of course it's not algebraic, because the kernel is discrete but infinite. And if it were a polynomial, then this would be a covering, and the covering group would be finite. But this is certainly infinite. So now put yourselves in the situation that you are under Wiles, you want to prove Van Allen theorem. This has been translated into a problem about elliptic curves. Aha, you say, now I'm done, because the whole theory of elliptic curves is given by the Varieties P function. But these elliptic curves live over Q, and you really want to know arithmetic properties of that curve. And arithmetic properties and this have absolutely nothing in common. So this is the big point where Tate comes in. But let me first show you a theorem. If you have a Being variety of the complex numbers, then there are two concepts which you can study, and one is the anamorphisms of A. Suppose that you get all polynomial maps from A to A, which map the group law into the group law. Well, you can imagine that's difficult. If I give you an exercise, here's my little curve in given form. Please compute all anamorphisms. And you don't know how to do it, it will be extremely hard, even for Philadelphia mathematicians. So the left-hand side is very complicated and difficult. The right-hand side is easy, because what do you have? You have a G-dimensional vector space, you have a lattice, and you compute all linear maps from L to L, just G by G matrices, which map the lattice to itself. So that's easy. You take the first base vector of the lattice, and that should land into the lattice, and then etc. etc. I mean, it's easy. So I want you to think of this is extremely easy. This is hard. Now, how do I prove this? So every mathematical talk should contain at least one proof. So let me try to do this for you. I have this here, and I have the analytic endomorphisms of this analytic variety. AC is an analytic variety, it has local charge, it's embedded in projective space, and so on and so on and so on. And clearly, this is an isomorphism. That's easy. It's clear that any endomorphism gives an endomorphism of the tangent space, gives maps lambda into lambda, and the map is just that if you have a map of L, the derivative of that map maps lambda into lambda, and this of course is an isomorphism, because as soon as you have this endomorphism here, you can really produce lambda L, then you have a map here, then you have d alpha here, and that gives you a map A here. Yeah? So this isomorphism this is easy. Right? Now I take the endomorphism of A and I have a natural map there, but of course to complexify it you get a map there. This is given by polynomials, and polynomials, somebody tells me, are holomorphic, so you can use them as holomorphic maps in analytic habits. Okay, now comes an important point, and if you understand this, you can walk out, and that's really obvious. If you try to produce a map from A1, from the affine space to affine space, right? And suppose you know locally it's analytic. Do you know it's algebraic? No, of course. The logarithm or the exponential or whatever, right? Locally it's beautiful analytic, but it's not algebraic. So there's no chance in general that algebraic maps and analytic maps are the same. Your feeling should be that here there are many, many more. Now there's a beautiful... so let me ask you a question. Here are the mathematicians all, right? If I say Gaga, what do you think? Do you think of a dress of meat, or do you think of something else? Okay. Chow and Serre, and certainly I should already mention many more names, prove that this is an isomorphism. So what is it basically? The graph of an endomorphism here sits in projective space cross projective space. That graph is locally analytic, but it's closed in its projective space. And the theorem by Chow and Serre is that something which is analytic and closed in projective space is algebraic. So that nasty thing that the logarithm is not a polynomial, not a quotient of polynomials, that happens because it has poles and so on. But that does not happen with these things. So, and that's called Gaga. And Gaga is a capital G-A-G-A, is Geometrie Analytique, is Geometrie Algebraic, a paper by Serre, and since then this has been website, that is Gaga. Of course, this is a deep theorem, so I didn't prove you anything. I just told you how to reduce this theorem to an existence. But this is essential in everything that's good. Okay, so here's the proof, and here's the remark. Compactness is essential. If you do this for affine line, there is an exponential map from the additive line to the multiplicative line, which certainly is not algebraic, but this is beautiful homomorphism, as you teach in your freshman calculus class. Here's another example. Take a product of GA and GM, that's the group. There's an isomorphism given by this matrix. It's a beautiful isomorphism, and certainly it's not algebraic. And Serre also gave another example. So here's the crucial remark. In some sense, analytic functions and algebraic number theory live in completely different worlds. Of course, mathematics is all together, but the beautiful techniques of the 19th century do not help us anything in algebraic number theory for this kind of questions. So now we are at the point on this borderline we finally decide the equation we're going to discuss. So here's the outline. I take it to be a variety. So on that basic example, I want to know what the torsion points are. And if this is the lattice, yeah, then here I draw the 3 torsion points. All intersection points now you see are 3 torsion, because if you multiply this point by 3, it becomes a lattice point. So you know that if you take an elliptic curve, yeah, and you view for the 3 torsion points, square bracket 3 means on the leading group the kernel multiplication by 3, then this is automatically z mod 3 plus z mod 3. So, in a sense, we know what the torsion is. And I give you an exercise to prove that canonically this kernel is isomorphic to this lambda over n times lambda. Do you see how to do it? Let me show you. You take lambda times to L to AC. Then you multiply down by n, so you get this 5 by 2 diagram with vertical arrows. You take the kernel on the right hand top side, and you take the co-kernel on the snake. And then you have the snake lemma, which just gives the rest. But you see, this really is canonical, and that's important. And that will be one of the central points of our ID. Do you still remember that this lambda either is a period lattice or it is a fundamental group? And that's important for everything what was going to follow. Okay, so to the Abelian variety, you can associate its torsion points. And now, these torsion points have an extra structure. Namely mine, I was working over some field, so I can use the Galois group. So I hope you can allow me to do that. You have your field K, think of the rational numbers. You have the algebraic closure of that, and the field homomorphisms, field holomorphisms, which keep the base field fixed pointwise. That's a group, and that group operates on the torsion points. How do you do? Well, the torsion points you get by solution of algebraic equations, so they live in the algebraic closure, the coordinates, and the Galois group commutes the elements of the algebraic closure, and that's the action. So this group here, over the complex numbers, it's just an easy group over 9. Over an arbitrary field, it's quite complicated. It might be that there are absolutely no rational points on E, which are 3 torsion, but if you go up your field a little bit, all of a sudden you see them. And how far you have to go up and which field you have to choose, that's one of the deep things in arithmetic geometry. So these groups, they have an action of the Galois group. And one way of phrasing it is to say that you have a representation of GK into this group of holomorphisms. That's one way of saying it. One detail which I'll completely ignore, if the group GK is a large group, it's a topological group, and this action should be continuous for that topology. On the left-hand side the topology, and the right-hand side the discrete topology. That's for the moment not very important. And one remark, the group scheme AN and the Galois module on the other hand are equivalent notions, so you can approach it from various sides. Okay, now the main point is that you take these points, and we did choose points on a real variety of complex numbers, but you can also do it over a finite field. Or you can do it over a number field and then reduce them up a finite prime or anything like that. So all of a sudden you have a huge variety of techniques. And then comes the important notion of a Tate module. So what I do, I fix a number L, which is different from the resonant characteristic. And I'm going to take together all the L power torsion points. So don't worry too much about this technical detail. I take one L, I take all powers of L, and I take all the power torsion points. So as a group of the algebraic closure, this is just Z mod L to the I, brackets to the power 2G. So it's a simple torsion group which is easy to understand. Much more difficult to understand is there's a Galois action on it. And the Galois action is completely given by the way this is embedded into A. Now you have to soup up all these data in one concept. And it doesn't matter so much how you do that. I mean, one way is taking the projective limit, one day is taking the inductive limit, and it comes all to the same thing, and don't worry about it. So if I say Tate module, you think of this gadget of all L power torsion points. All L power torsion points. Now all L power torsion point is dense, so everything you do on the L power torsion points, right, uniquely determines what you're doing. Okay, well, here is the explanation. TL is just in the projective limit, ZL is the analytic numbers, and the element in TL is a sequence, is a coherent sequence of. So this is L torsion, this is L squared torsion, this is L to the I torsion, and so on, so on, so on. Okay, now we come to the main point. Classically, we had the Abelian variety of complex numbers, and we considered this period lattice. Plus, now comes the important point, the complex structure of lambda times R, tensor R. Yeah? And that's, we love to do, now we have complex analysis available, and so on, and so on, and so on. Now comes the beautiful idea of Tate. Take the classical approach, but completely forget this C structure. But remember the structure as a Galois module. So the Galois structure is an algebraic structure, and you don't know anymore whether 2 points are close or far away, but you do know which are permuted by the Galois group. So you completely forget about the metric, but you remember the algebraic structure. Now you must immediately see and recognize that this works over any field. So if I work over a finite field, I can work over a field with 2 elements, there will be a variety there. There's no complexification, there's no lattice, there's nothing like that. The torsion points are there, and the Galois group is there, and I know exactly what I have, right? Okay, and now comes a beautiful theorem, and that's this theorem. In the classical case, we had that the endomorphisms of A are computed by the linear maps which map lambda into lambda. Okay, now we forget about this, and now we work with an arbitrary field. We take a prime L, which is not the characteristic of K, and we take the endomorphism of A, and we should like to compute it. Well, this group maps to the endomorphism ring of TLA. Because an endomorphism that maps torsion points to torsion points, and so on, and so on, and so on. Now the map from left to right is natural and certainly injective. Because if you have an endomorphism, and if it is 0 of all L power torsion on a dense subset, then it is 0. So the map from left to right is injective. But there's no way that these two can be isomorphic. But what you can do, if you can write tensor ZL and then map this. And the Tate conjecture says that this is isomorphism. So that's the conjecture Tate made. And you only have to have an Abelian variety of any field think of a number field, think of a finite field or anything like that, but you want that the field is a finite type over P. Finite type means it's a finite extension, transcendental and a finite algebraic extension. And of course every real variety is defined over a finite type because it's given by a finite number of equations. The finite number of equations is a finite number of coefficients. You soup up all the coefficients in your base field and it's defined over that field. And note that any field of finite type has a huge Galois group. For example, any field of finite type, the roots of unity are finite. So the cyclotomic field Galois group, which is very, very large. So you should think that this field of finite type, P is its prime field, it's either Fp or Q. You should think of that this implies that Gk is the Galois group of K bar, of K, I want to write the automorphism group, is large. So there's a large group operating on this Tate module, and what the theorem says, or the conjecture says, that if you take the Tate module, you take anamorphisms. Now first of all, these are just 2G by 2G matrices over ZL, so that's easy. But mind, they should commute with the action by this GK. And then the theorem says that everything which commutes with this action is exactly the same as the anamorphism of A over tensor ZL. So do you see this beautiful idea? The beauty of the idea really is in the transition from here to here. You forget the complex structure, you remember the Galois structure, then you want to compute the anamorphisms. Okay, Tate says, take all anamorphisms of your Tate module, invariant under Galois, and these should be algebraic. Up to tensor remotes. And of course this is a deep theorem, but here you see exactly the analogy. Do you remember how I went from here to here? This was Gaga, not Lady Gaga, but Charles Sarah Gaga. Do you see how we should go from here to here? Well, that's properties of the Galois module. Okay, so this was the conjecture Tate made in 1966. And this is the definition of a finite field of finite type. There are examples, number field, a function field of one previous field, a field of finite type of finite that is a large absolute Galois group, and so on and so on. To give an example where K is not finite of finite type, where the conclusion of the conjecture does not hold. Well, that's easy. Given the being variety of the complex numbers, the Galois group is trivial. And then this side is extremely large, where this side is very okay. Here's an exercise. Start. That's for the experts. You take two elliptic curves, and you want to prove that this is an isomorphism. This was an exercise which David Mumford solved in 1962. Talked to Tate, and it was the basis of the whole thing. To the experts in the audience, I give you an exercise to prove this. Okay, here's the theorem, which Tate proved in 1966, which Falcon proved in 1983. Namely, the Tate conjecture for a being variety is true. And that has a long, long history. Tate wrote a beautiful paper. His papers are always concise and contain everything you like. And moreover, it gives you access to new methods, to a very general theory, and so on and so on. And that's a beautiful paper, 1966.
Did Tate formulate the conjecture in Dutch?
Excuse me?
Did Tate formulate the conjecture in Dutch?
No. No, it's there in Dutch, but it's okay.
It's very Dutch.
Before isomorphism.
Ah, yeah,
Yeah.
There are two misprints in my slides, and you spotted the first. Please find the second.
Where the previous?
It came before.
Okay. I copied it from the survey paper.
And what should the word be?
One. So I said N, but A means one. Okay, thank you very much for notifying. And this theorem, Tate proved in 1966, Zarhin and Mori proved the function field and positive characteristic. Serre proved for a special case of elliptic curves of another field. So all that time, people were really working on it, and then it was the genius Varieties who solved 3 conjectures at one stroke, and the Tate conjecture was one of them, and it was really the tool to do all the other things. But this theorem by Tate over finite fields was a shock to all of us, that you can really prove something about the endomorphism ring over a finite field. I mean, how would you ever do that? I mean, there's no way of sitting down and writing down. Doring in 1941 described this for elliptic curves, and that's a long paper. It's very technical, very difficult, hard to read, even if you know German. But Tate proves it in a very short paper, all at once. So here's an easy example. Suppose that your Galois group acts diagonally. So all elements of your Galois group act by matrices which are 0 off the diagonal and equal elements on the diagonal. Then, of course, the Galois action is not very difficult here. Then this has rank 4. So then the endomorphism ring has rank 4, the elliptic curve, which is possible in characteristic P, which was studied already by Doring. But you immediately now see what you have to do. Because if this has rank 4, then the Galois group should commute with every element in this matrix. So should act in diagonal form. So should be in this form. So this really explains all the classical results. Okay, Tate in 1962, published in 1965, wrote a beautiful paper, Algebraic cycles and polar zeta functions. And he generalized this conjecture widely. He generalized this conjecture in the Étale cohomology into cycles. And the main issue is that if you have a cycle in the Étale cohomology invariant on the Galois, then it should be algebraic. And once you see this, of course, you get excited. You weren't already. Because what does Hodge theory say? The Hodge conjecture said if you have an analytic cycle, right, invariant on subject, then it should be algebraic. And already in his 65 paper, Tate says that his conjecture had the flavor of some connection with the Hodge conjecture. And in fact, that connection was proved by Pullman, by Milne, and later in full generality by Lehm for abelian varieties. So they prove for abelian varieties the analog of the Hodge conjecture, which in this case is the Tate conjecture. And specialists really believe that if you formulate the Tate conjecture correctly and you prove it, then you prove the Hodge conjecture. So all of a sudden this concept, this simple concept of forgetting the complex structure, but remembering the Galois structure, all of a sudden puts all mathematics like Hodge conjecture and Virgin and Dyer and so on in one stroke. So that's what I wanted to tell you, that Tate really created the new tools for us to do mathematics. So let's do mathematics. Thank you very much.
We're certainly open for questions.
So you were talking about this early case that was worked out by Düring or something in 41.
Yes.
So at that point, he phrased it in terms of the Tate module, so to speak?
No, he phrased it in terms of elliptic curves, and what you need to know is if you have an elliptic curve, you have an endomorphism, it's all defined over a finite field, then it can be listed to characteristic 0. And so that is all phrased before using Tate modules and whatsoever.
I see.
So there's no, at that point there was no connection. And I think before 1961, well, that's not true. I mean, one of the criticisms I was expecting is that Tate was not the first to use Galois representations. I mean, the braid groups by many of the Japanese mathematicians already did a lot of this thing. The Tate module, in fact, is completely encoded in the 1961 Grothendieck fundamental group. So if you read Grothendieck carefully, you can encode, you can decipher the Tate module. So certainly Tate was not the first to consider a Galois representation. Certainly he was not the first to note that the fundamental group in the Wave variety looks like a fundamental group, right? Certainly not. But the way he used it and the way he formulated this, I mean, this idea, I think, was completely novel. So that, no, as far as I know, Dory never considered Tate modules and things like that. Yes.
This is a little more murky than that. Namely the following. Grothendieck was working on SJ1, the fundamental group in algebraic geometry. At the time he came to Harvard in 59, spent a year, 59, 60.
Yeah.
Spent a year. He, well, of course, talked with Tate a lot. Tate had a seminar in which he talked about Galois cohomology, which is the Galois cohomology in just the case of a point.
Yeah.
Okay. Oh, and he worked out all the details which helped Grothendieck formulate everything correctly. And knowing Tate, already that must have dawned on him. So it's not clear to me, not a question of priority.
No.
It's a question already of, it's murky how these things develop. I think it was in the air because they were talking about this already a lot.
I would prefer in the air instead of murky. Sure. No, you're right, you're right. But certainly Doring had nothing like this.
41, sure.
Yeah, 1941.
Look at Doring.
I really do hope that you understood that when Tate got his Abel Prize, that it was just rephrasing a classical concept like a lattice, period lattice, into a Tate module. All of a sudden gives a flow of potent and beautiful results and new views on mathematics.
Other questions, comments? Thank you.